here and move to our second objective. This is really speaking about enzymes and understanding the role of enzymes in chemical reactions. And so we're going to speak about why they're important, but I also want to reiterate that enzymes are proteins. Okay, they're examples of proteins. They have a really important function of speeding up and catalyzing reactions in our body, but at the core, they are proteins. And so they need to exist in a specific environment in terms of not being denatured or destructured. Otherwise, we're going to lose that function if we denature that structure. Anyone remember what level of structure is interrupted or disfigured when we have denaturing of proteins?
Is it the second?
Yep, excellent. So the secondary structure is what we interrupt or disfigure when we introduce proteins to excess heat, excess acidity, and things like that. Now, enzymes are proteins. They catalyze reactions in our biological systems. They are catalysts in that they speed up the rate of the reaction. And so they just make a reaction more favorable, more likely to occur and to progress faster. They do so by decreasing the activation energy for a specific chemical reaction. Okay, and when I say that they decrease the activation energy, they make it easier for the reaction to progress. When you talk about what the activation energy is, it's the energy barrier that must be overcome in order to drive that reaction. And so if I lower that energy threshold, if I lower how much energy is required to drive this reaction, I'm going to make it more favorable, more easy, more likely, faster for that reaction to take place. Okay. So they basically bind to a reactant, which we can also call a substrate. And then on the other end, through this bidirectional relationship here, we have the enzyme and substrate complex. And on the other end, we pretty much kind of spit out the product and then the enzyme as well. And so we can think about enzyme plus substrate gives us that enzyme substrate complex. And then on the other end, we spit out the product, which is what that driving of the reaction is. And then we spit out the enzyme as well. We can think about this in the reverse way as well. So if I want to go from product back to substrate, I can do so with an enzyme as well. So I simply bind that product to my enzyme, and then via this enzyme product, enzyme substrate sort of intermediate, I will then on the other end end up with my enzyme and my substrate as well. So we can think about this reaction as occurring in the forward direction and in the reverse direction as well. Let's speak about that activation barrier that we kind of introduced earlier. So the activation barrier is the energy requirements of a reaction. And so if we compare the energy requirements here on the y-axis to the reaction coordinate, and we can kind of substitute reaction coordinate with the time it takes for this reaction to occur, okay? So basically energy requirements compared to time. And we look at an initial curve here. So the curve A represents how the reaction would proceed in the absence of the enzyme. And as we can see, it's going to take a lot of energy for this reaction to occur. So the activation barrier is pretty high. This is how much energy is going to be required in order to drive this reaction from reactants here on the left to products here on the right. And an example that we're using here is if we combine carbon dioxide and water, that gives us carbonic acid here, okay, H2CO3. If we were to try to achieve this reaction with an enzyme present, what we'll see is the curve in blue, that the energy requirement is significantly lowered. In other words, the energy or the activation barrier is significantly lowered. And so we can drive this reaction with much less energy, with much less of an energy requirement or energy demand, okay? And this is what we mean by saying that an enzyme lowers the activation barrier, makes it more easier, more favorable, more likely for a reaction to proceed, okay? And so we can look at the difference here between the curve of our standard energy levels versus how much energy was required in the presence of the enzyme. And we can compare that to almost twice as much energy required in the absence of that enzyme, okay?
I have a question.
Yep, sure.
So are we technically, you don't need an enzyme for a reaction, it just makes it faster?
So the enzyme, we do need enzymes for the reactions, yeah. But a reaction can proceed. It's just a way of expressing how the enzyme changes the way that a reaction proceeds, if that makes sense.
Okay, so it's just kind of like how it impacts it.
Right, how it impacts that reaction. Yeah.
Okay, thank you.
Yep, sure. Any other questions about this before we move on? Okay. And just to kind of reiterate there again, so using this example of CO2 and water, now together over time, these two could become carbonic acid. It would be very hard, very difficult. It would take a lot of time and a lot of energy, but an enzyme present just speeds that up, makes it more likely, more favorable, kind of more spontaneous, if you will, and then we produce that carbonic acid more easily. Okay, just to kind of differentiate how this can happen and what we mean by saying that it can proceed without the enzyme present. Okay. Let's talk about how this specificity is achieved with enzyme binding. So as you would imagine, we've got lots of different enzymes in our body. We've got GI enzymes, we've got reproductive enzymes, urinary enzymes, lots of different examples throughout our various systems. And so there needs to be some way to mark a specific enzyme as binding to a specific substrate. This is what we refer to as substrate specificity. And so this is protective, as you would imagine, also efficient, right? So that all of our enzymes are not being bound by all types of inappropriate substrates. And so that's why we have this specificity. Now, the way that we describe the specificity is not all that clear. And so there are two ideas or two schools of thought or two theories or two models, if you will, about how that specificity is brought about. The first theory or model is the lock and key model, okay? And then this, to explain this model, this model kind of indicates that we have a substrate here on the left, so substrate A, we've got substrate B, substrate C, and substrate D. And so what this model theorizes or suggests is that substrate C has a specific shape, and so only substrate C can physically bind to this enzyme, okay? So only substrate C will be able to fit in the active site to activate or turn on this enzyme. And so this explains how we get specificity on one end, but it doesn't explain the reversibility of most enzymatic reactions. And if you remember me mentioning earlier, reactions can proceed in the forward direction, but we can also have the product bind to the enzyme, and it should give us back our substrate on the other end, okay? And so that is not explained by this lock and key model, right? If the product is going to look different from the substrate, how will we then have that product bind or fit into that very specific enzyme again, okay? So while this model, the lock and key model, is great at explaining the specificity, it doesn't quite address the reversibility of enzymatic reactions. The second model, which is called the induced fit model, is a little bit more fitting at explaining not only the specificity of that binding, but the reversibility of the overall reaction. So we've got a substrate, such as substrate S here. Now, enzyme E can not necessarily have a specific lock and key shape to begin with that matches substrate. And so what happens is there's an induced fit. When the substrate gets really close to the enzyme, it's going to induce a fit. It's going to encourage or manipulate the enzyme into shaping or accommodating its shape. And then that will allow it to bind, and that will give us the product on the other end. Likewise, when the product gets close to the enzyme, that will induce a fit. So it's going to manipulate the enzyme to change its shape to accommodate that product. And so we can have the enzyme bind to the product, and then the reaction can proceed in the reverse direction. So the induced fit model is much better at explaining how we have that initial specificity of substrate binding to enzyme and giving us product on one end, but it also gives us a way to explain or rationalize that we have a product binding to an enzyme and giving us substrate on the other end. Now, again, these are models or theory. This hasn't actually been, concretely defined or identified, but these are just various models that have been presented that would explain how we have this substrate specific binding where only a specific substrate or product can activate specific enzymes, okay? All right, so let me watch the time. Let's talk about cofactors and coenzymes. So cofactors are non-protein components of enzymes that are required to hold their functional conformation, okay? So they're non-organic compounds, things like magnesium, copper, zinc, iron, and they're important in terms of holding the functional conformation of the enzymes as they function, okay? So essentially, cofactors are a really important part of the reaction. The reaction cannot happen without cofactors. Let's put it that way. Let's talk about coenzymes and kind of contrast cofactors to coenzymes. Excuse me. So coenzymes, on the other hand, have no catalytic activity. They're not necessarily important as such for the functioning of the enzyme, but they're necessary for the enzyme to participate in the reaction, okay? These can be vitamins and other types of coenzymes, which we'll talk about some examples later on. But essentially, the way that I like to explain this in terms of a practical example is if you think about your car. So you're driving a car. In the car, you've got the steering wheel, you've got the headrest, okay? The steering wheel is vital to the function of driving. I cannot drive the car without the steering wheel present, okay? That would be an example of a cofactor, okay? On the other end, we've got something like the coenzyme. While it's kind of important, it's going to help support the whole process, it's going to keep you comfortable at the very least, it's not essential to driving the car. It's not an essential function to this happening, okay? It just helps to support it and to support the function of that enzyme, okay? And I don't want you to think that they're not important. They are important. They do help the reaction, but then they don't have any catalytic activity. The reaction as such does not rely in any way on coenzymes. They just help to support the process, if you will. Okay. Let's talk about some of the things that affect the reaction rate. Now, the reaction rate can be affected by a couple of different factors, but it's essentially how many molecules are generated per unit time. So how fast can I go from substrate to product? That's going to be the catalytic rate of an enzyme. If it can produce 10 units of a product in a minute, that's going to be one set rate, but a faster catalytic rate would be if it can produce 100 units of a product or 100 molecules of a product per unit time. And so that's what we refer to when we speak about this enzyme, this enzyme's catalytic rate. That will be determined or affected by, one, the substrate concentration, which kind of makes sense, right? If I have more substrate to begin with, I'm going to be able to create more product faster because I just have more stuff to work with kind of sitting on tap, if that makes sense. So more substrate concentration or higher substrate concentration translates to a faster catalytic rate because we have more substrate readily available, readily accessible to be turned into product. The second factor that affects the catalytic rate is the enzyme concentration, which again really makes sense, right? If I've got more enzyme lingering around, I can also increase the rate of production of product, the rate of molecules generated per unit time. So more substrate, faster catalytic rate, more enzyme, faster catalytic rate as well. The other two factors that influence the catalytic rate are the affinity of the enzyme for the substrate. And when we speak about affinity, affinity means affiliation, attraction, how likely, how attracted are the enzyme and substrate to each other. And that can slightly change depending on quite a few different factors. But the enzyme can be really attracted or really affiliated to the substrate in one state, or it can have a lower affiliation in another state. And one example that comes to mind is one of the molecules that moves our muscle. So in the presence of lots of calcium, myosin, which is one of the proteins that moves our muscle, really has a strong attraction, a strong affiliation to its neighboring enzyme, which is actin. In the absence of calcium, Myosin and actin have an aversion. They're not attracted to each other at all. And so that's an example to tell us about this affinity or this attraction between enzyme and substrate. And that, as we would imagine, would obviously also influence the catalytic rate. The fourth factor is temperature and pH, and temperature ties into what we said already. Because enzymes are proteins and because they need to be in a specific environment as far as their temperature exposure, how much acidity they're exposed to, if we have a lot of heat, we can actually drive the reaction faster to a point, right? Remember, we're going to denature proteins beyond a certain temperature, but just having more heat, we're going to increase the energy that's seen within molecules in general. And so they're going to bombard or bump into each other at a faster rate because they just have more energy in terms of their movement. And so we see that if we increase pH, if we increase temperature, we can increase the catalytic rate to a point, okay? Beyond that point, we will denature the protein and we will obviously lose function. Okay. Let's speak about regulation of enzyme activity. I kind of alluded to this earlier, but we need to be able to regulate how our enzymes are turned on and off. And that just makes sense. We don't want enzymes kind of running indefinitely. We don't want them running around our cells and our body, binding to anything, just completely unregulated. But we need to be able to regulate enzymes. In other words, turn them on and turn them off. So we've got 4 mechanisms that kind of determine or dictate how we can bring about that enzyme regulation. So the first one is allosteric regulation. And this is basically the idea that we've got a modulator that basically binds to the enzyme at a site that's different from the active site. We're going to call this the regulatory site. So remember, the substrate is what binds to the active site. The regulatory site is what is thought to bind this modulator. And so the modulator can say, turn the enzyme on and allow it to bind substrate, or turn the enzyme off and prevent it from binding substrate. So that's one way that we can regulate enzyme activity. And when I say regulation, in your head, just think, turn it on, turn it off. Turn it on when it's needed, turn it off when it's not, okay? And so allosteric regulation is kind of one example of that regulation. The second example is a little bit more complex. This is called covalent regulation. And covalent regulation is where we have a chemical group. And I want to use the example of a phosphate here because a phosphate is the most common chemical group that we see partake in this covalent regulation. And so essentially we've got the enzyme in its deactivated state. We've got the enzyme in an alternative state. And so when we bind the chemical group to the enzyme, it's going to be in one state. If the enzyme does not have this chemical group, it's going to be in the opposite state. And so this is how we can turn the enzyme on and turn the enzyme off with another enzyme. So the other enzyme in question here is enzyme A and enzyme B. And essentially enzyme A puts that covalent bond onto our enzyme that we're trying to regulate, whereas enzyme B, another enzyme, takes that covalent bond or takes that chemical group off of the enzyme that we're trying to regulate. So a simplistic way to view this is that we have another enzyme that's helping to regulate our enzyme in question. It can add that chemical group, which will either turn the enzyme on or off. And I'm saying turn it on or off because we see a lot of different examples. Sometimes adding a phosphate turns an enzyme on. Sometimes adding a phosphate in other systems and other processes turns it off. And so the regulation can be in either direction, but simply using this third-party enzyme to add a chemical group to our enzyme that we're regulating will change its state, and then using another third-party enzyme to remove that chemical group from the enzyme we're trying to regulate will put it in the alternative state, okay? And a really good example is this example here. So protein kinase and phosphate as that chemical group. And so what we see is that we've got enzyme plus that phosphate. So this is the enzyme that we are trying to regulate. So I'll call this enzyme X. Enzyme X plus the phosphate, which is that chemical group bound to it. Remember, protein kinase is our third-party enzyme that is going to add that phosphate to our regulatory enzyme, enzyme X. And then we're going to get this enzyme with that phosphate bound to it. Now, this can be either activating or deactivating the enzyme, depending on which system we're in. On the other end, the other third-party enzyme, which in this case is a phosphatase, that is going to remove that phosphate from our regulated enzyme, enzyme X. And so it's going to put the enzyme in the opposite state by removing that phosphate, okay? And this is something we're going to continue to see throughout various systems. When we look at muscle, when we look at neurons and so on. Basically, when we see kinase in the word, anytime you see the word kinase, this is adding a phosphate, and that is going to do something to regulate that enzyme, okay? The opposite is true. Anytime we see the word phosphatase, that is cleaving a phosphate, and that is also going to regulate in the opposite direction. So protein kinase adds a phosphate, which may turn something on or off. Phosphatase removes a phosphate, which may turn something again on or off, but it's going to be the opposite of what protein kinase achieved. All right.